AI tool for programming quantum computers. Executive summary. An AI-powered assistant for quantum programming could simplify the complex world of quantum computing by translating natural language into code, automating algorithm design, debugging, and optimization. It would integrate quantum and classical systems, support secure cryptography, and run on multiple hardware platforms. By embedding into common development tools and ensuring ethical, transparent design, this system would democratize access to quantum technology, making advanced computing practical, efficient, and widely usable. Article: Quantum computing is advancing quickly, promising to solve problems beyond the reach of today's computers. However, programming quantum systems is extremely challenging due to their mathematical and technical complexity. To bridge this gap, researchers are developing tools that use artificial intelligence AI to help write, optimize, and debug quantum code. An AI assistant like this could make quantum programming far more accessible, transforming complex theory into practical, usable software. 1. Talking to quantum computers in plain language. The most exciting feature of this tool would be its ability to turn natural language, ordinary speech, into functional quantum programs. Instead of memorizing specialized syntax, a user could describe their goal in simple terms. For example, simulate a 5-qubit teleportation circuit, or design a version of Shor's algorithm. The AI would then translate this request into working code using frameworks like Qiskit, Cirq, or Q. Trained on libraries of existing algorithms, the AI could identify the best methods for each task and automatically generate both quantum and classical components. In effect, it turns English into a new programming language for quantum computing. This reduces the learning curve dramatically and allows students, researchers, and developers to experiment with quantum systems without deep expertise in quantum mechanics. 2. Blending quantum and classical computing. Most practical quantum applications are hybrid, meaning they combine quantum processors with classical CPUs or GPUs. The classical parts handle data preparation and post-processing, while quantum hardware performs specialized calculations. The AI assistant would act as a coordinator, dividing work between systems, converting data between bits and qubits, and managing synchronization. For example, in the variational quantum eigensolver, VQE, a method used for molecular modeling, the AI could control the loop between classical optimizers and quantum circuits, ensuring smooth communication. It would also make code hardware independent, adapting it to run efficiently on platforms like IBM-Q, IonQ, or NVIDIA-CUDA-Q. By handling hardware constraints automatically, developers could write once, run anywhere, saving time and effort. 3. Designing and improving quantum algorithms. Beyond writing code, the AI could design and optimize algorithms for specific problems. Given a challenge, such as optimizing roots or simulating molecules, it could propose suitable quantum approaches like Grover's search, QAOA, or custom hybrid methods. Once the algorithm is chosen, the assistant would refine it to fit the target hardware. It could reduce circuit depth, minimize gate count, and adapt to the device's noise characteristics. Using reinforcement learning and advanced compilation techniques, the AI could evolve circuits over time, much like a self-improving compiler for quantum programs. 4. Smarter debugging and simulation. Debugging quantum programs is difficult because observing a quantum state destroys it. To solve this, the AI would integrate quantum simulators that mimic qubit behavior. Developers could visualize states, monitor gate sequences, and validate outputs step by step before deploying to actual hardware. If an error occurs, users could ask conversational questions like, "Why was T for the RM warbis twirrs? Why is the error rate 60%?" The assistant could analyze the circuit and identify causes such as wrong gate order, noise interference, or calibration drift. It might even fix problems automatically using machine learning-based error correction. This hands-on guided debugging experience would make learning and experimentation much easier. 5. Quantum cryptography and security. Quantum computing has major implications for cybersecurity. The AI assistant could simplify the creation of quantum cryptography systems, such as quantum key distribution QKD. In these systems, encryption keys are shared through quantum channels, making eavesdropping detectable. The AI could automatically generate the sender and receiver logic, simulate the communication process, and test security against potential attacks. It could also integrate post-quantum cryptography (PQC), classical encryption methods that resist quantum-based attacks. Examples include lattice-based or code-based algorithms. The assistant could benchmark different schemes, balancing performance and security, and even design hybrid QKD-PQC systems that remain secure as quantum computers grow stronger. 6. Secure multi-party computation. The AI could also make secure multi-party computation (SMPC) and distributed quantum protocols easier to implement. These allow several participants to work together without exposing private data, useful for tasks like secret sharing, voting, or collaborative research. The assistant could generate and coordinate all code components, simulate message exchanges, and verify that communication remains secure. This would make complex cryptographic projects accessible to general developers, not just quantum specialists. 7. Integration with coding tools and cloud platforms. For real-world use, accessibility is key. The AI assistant would integrate with popular development tools such as Visual Studio Code and Jupyter Notebooks, acting like a quantum-focused version of GitHub Copilot. It could provide real-time code suggestions, explain errors, and generate documentation automatically. The tool would also connect to major cloud platforms like IBM Quantum, Azure Quantum, and AWS Braket to run programs directly on real quantum machines. It could handle back-end selection, job scheduling, and results visualization. For collaborative teams, the assistant could maintain shared notebooks, track versions, and document experiments automatically. As hardware evolves, it would adapt its optimization strategies to maintain top performance. 8. Ethics, security, and transparency. Because the assistant would interface with sensitive systems, security and ethics must be priorities. It should use strong encryption for credentials and protect access to quantum hardware. Every action would be logged transparently, with readable documentation explaining what the AI did and why. The assistant could also flag ethical or privacy concerns, especially in cryptographic contexts. It might warn users about risky data handling or highlight algorithmic bias. Built-in version control would ensure reproducibility, linking every code update to its simulation results for full traceability. 9. The future of AI and quantum computing. The merging of AI and quantum computing represents a powerful new direction in technology. As language models improve, their ability to understand quantum mechanics and circuit logic will expand. Early systems like Microsoft's Q Copilot and IBM's Qiskit Code Assistant already hint at what's possible. In the near future, AI tools could manage complete hybrid workflows, writing, optimizing, and testing quantum code with minimal human input. Such tools will make quantum computing practical for engineers, not just physicists. By simplifying access and automating complex steps, they will accelerate progress in science, cybersecurity, and advanced computing. Ultimately, an AI-powered quantum assistant would democratize quantum programming, making it a normal part of everyday software development. By combining intelligence, automation, and ethical design, it would help create a world where quantum technology is not only powerful, but also understandable, secure, and widely available. Conclusion: an AI-driven quantum programming assistant could transform how humans interact with quantum systems. By blending natural language, algorithmic intelligence, and secure automation, it connects theory to real-world development. Such a tool would make quantum computing practical, efficient, and accessible. This would lay the foundation for a future where AI and quantum technology advance together to solve some of the world's most complex problems.